Hi, this is Troy Hunt. I'd like to walk you through a really brief demo on how to discover some of the kind of crazy things that your mobile devices are doing when they talk to the internet. I recently published a very popular Pluralsight course called Hack Your API First, which goes into a lot more detail about the crazy things you can find behind apps when it comes to security, and importantly for developers, how they can protect their apps from very easily discoverable risks. So there's a heap more info in that course. This is going to be the lightweight intro. Now I think most people who use modern devices like the ones we see here on the screen are probably aware that many of the apps that you download and install today from app stores like Apple's App Store or Google Play communicate to services on the internet. Now they do this using the same protocol as your browser does. The difference is though, rather than seeing URLs in the address bar and having comparatively quite a bit of visibility into where the app is loading from and who it's talking to, rich client apps such as you'd find on mobile devices communicate over the internet using APIs. Now what a lot of people don't know is that even though when you open your favorite apps, you can't really see what address they're communicating to or what data they're sending backwards and forwards, you can actually easily discover it, and it only takes a couple of minutes of setup with free tools. So what I wanted to do is just a really quick walkthrough of what's involved in setting that up, and then I'll show you a couple of the really crazy things that you can find just by looking at the way your apps are communicating. I'm going to be using Fiddler for this. For many software developers, Fiddler will already be a familiar tool. It's a great HTTP proxy and debugging tool. What a lot of people who use Fiddler regularly might not know though, is that Fiddler can also act as a remote proxy for your mobile devices. So that's what I want to show you how to set up now. So here we are in Fiddler, and all I'm going to do is jump up to Tools, head on down to Fiddler Options, and I'm going to go over to the Connections tab. Now there are a couple of things here to take note of. Number one, allow remote connections. You will need Fiddler to be restarted for this to take effect. We'll do that shortly. Number two, the default port. Fiddler will listen on port 8888. We'll come back to that a little bit later. We also want to check out the HTTPS tab. Now there's a couple of things we're going to do here. The first is we'll capture HTTPS connects. So this is the beginning of the handshake for an HTTPS connection. We're also going to decrypt HTTPS traffic. And when we do this, you'll see an alert box pop up here that says scary text ahead. Now here's the thing with HTTPS decryption. We're not really breaking the encryption. What we're going to do is allow Fiddler to intercept it and then re-sign it with its own certificate. When we checked that box, Fiddler has now prompted us to explain that it's going to generate a unique root certificate. This root certificate needs to be installed on the PC that Fiddler is running on. I go into more detail on why that's important in the course. But for now, we're just going to trust that certificate and move on. More security warnings, which should give you an indication of how significant this is. And just for good measure, yet another confirmation. And it's done. We now have Fiddler's root certificate installed on the machine. Let's now go OK to that, restart Fiddler, and that's that side of the equation done. The next thing is, I want to walk you through the process for setting up an iOS device to actually proxy its traffic through Fiddler. Other device manufacturers have different approaches to the way they implement proxies. So if you don't have an iPhone or an iPad, a quick Google should answer that one for you. Let me walk you through iOS. I'm just going to jump over to my Wi-Fi settings, and next to the network I'm connected on, we'll see a little information button. we'll hit that guy and we'll slide into the Wi-Fi network details. Down the bottom, there are some HTTP proxy settings. We're going to hit manual. Now, in the server field, we want to enter the IP address of your machine running Fiddler. If you're unsure of how to do that, either do a quick Google or fire up a command prompt and enter ipconfig. So that's what I've just entered. In the port, we're entering the port that we saw on the Connections tab in Fiddler. It'll default to 8888. So unless you've changed it, that's what will go into your proxy configuration. That's it. The iOS device is now going to send all of its traffic through Fiddler. So let's go and open up something interesting and see what happens. I'm going to open up the Evo Car Magazine application on my iPad. It looks like this guy just here. It's a fantastic magazine. I love it, but it does some really screwy things in terms of the way it communicates with the web. Let me show you what I mean. I'm just opening the app on my iPad now, and what we can see is a whole bunch of requests now appearing in Fiddler. So we can see the host for a lot of these ends in evo.co.uk. Every single one of these rows here is an HTTP request being initiated from that app. If we look at the content type column, we'll see a lot of these are JPEGs, so the images. We'll also see some JSON responses. So now we're looking at actual data returned from APIs. Now what you will see is that there are quite a lot of requests here. It's going on and on and on. And this is the odd thing that I want to show you about this app. In fact, it's so odd, the only way I can really show you is to pause here, let it keep going for about another hour, and then we'll come back and I'll show you what I mean. So I went away, had some dinner, came back and found this. 523 requests from the Evo app. There might be a few there from other background processes on the iPad, but the vast majority are Evo. And there's a really odd reason for that I'm going to show you now. But first of all, I'm going to scroll back up to the top and we can see the first requests here. Here's one to editions.xml. So it's probably going to be a data file. Let's go over to the Inspectors tab. We'll decode this because it was gzipped, which is a good thing. And then because it's XML data, we'll just click on the XML tab and we get a nice little structured tree of what the data is. So this is a pretty typical example of a response from an API. And the significance that I want to point out here is that we can now see the internals of how this app is communicating to a backend service. And we can see a fairly typical sort of structure here as well. But here's what I really wanted to show you in terms of the oddity that this app displays. Let's sort the requests by the response size of the body. So in this case, it's going to sort from the smallest to the largest. Now, if we scroll all the way down to the bottom, take a look at these guys. That one down the bottom is 75 million bytes. In other words, a little bit less than 75 megabytes. And there are heaps of them too. You can see dozens and dozens of requests here. All of the rows that you can see on the screen here range anywhere from 15 meg up to 75 meg. They are huge responses. Now remember, this is a mobile app running on my iPad. This is chewing up my data, potentially my very expensive data. We can scroll down a little bit over here and see the response headers. It's not telling us a whole lot there. We can see that it is actually a zip content type, so for some reason it's downloading massive zips. Let's now sort the results by host, because I want to get all of the evo.co.uk ones together. I'm now going to go through, I'm going to select the bottom one, scroll back up to the top, and let's select all of these evo.co.uk hosts. Let's take a look at the Statistics tab. Now here's what's really interesting. We have got about 1.8 gigabytes worth of zip files downloaded by this app on my iPad. 1.8 gig. That is ginormous. That's a lot just to fit on my iPad with limited capacity, let alone suck down over my connection. Now that's across 190 separate HTTP requests. A lot of requests downloading some pretty big files. It also includes well over 8 megabytes worth of JPEGs, so clearly some pretty chunky images coming down the wire. Now here's a trick we can do. At the end of the day, all of these are just HTTP requests. Let's go and take a look at one of these images. So we can go down and select something with an image content type, and in this case we might actually pick a PNG. So why have we got a 0.5 meg PNG down here? Let's take a look at it. We'll select that guy, jump on over to the image view, and we get a representation of a nice Ferrari 360, but it is over 0.5 megabyte in size. And it's not actually that big either, 768 by 512, or at least the dimensions aren't that big. The problem is that PNG is just not the right format for this sort of image. It really should be a JPEG. In fact, we can see the difference of how inefficient that PNG is compared to the JPEG just by selecting the image above it. So this one is about 80K less, and it's actually significantly larger in terms of dimensions. So much more efficient pixels saved as a JPEG. But here's the other thing we can do. Because all of these requests are just HTTP requests, we can scroll down, grab one we're interested in, so we'll grab one of those big zips, right click on it, go down to copy, and grab the URL. Now this is just an HTTP address. We can kind of see it here between the host and the URL columns. Let's now just jump over to Chrome, we'll plug that into the address bar, and we can just download it. Bit of a security observation here as well. If I can just grab a URL like this and paste it into the address bar, then clearly there is no authorization required on it. I'm just an anonymous user in Chrome when I plug that address in. But it's downloading. It's going to take a while because it's 72 megabytes. So let's let that download and then I'll come back to it a little bit later. Somewhere around 20 minutes later, our 74 megabyte plus file has finally downloaded. And remember, that is one of dozens and dozens of files that are dozens and dozens of megabytes in size. All of them sucked down just by virtue of opening up the EvoMag app. So let's take a look at what's inside this zip. So first thing is there's a data folder, only one folder. Let's take a look in that guy. We've now got 46 separate folders ordered numerically, so this is starting to look like some sort of sequence of data. So we might just drill down into the first one of those, and we've got an assets folder and an index.manifest file. Let's maybe take a look inside that manifest. We'll just open it up in a text editor, just out of curiosity. And fortunately it's just a plain text file, so we can have a look at what's inside it. No structured data. It's not JSON or XML, it's some sort of proprietary format. And inevitably, this is just a meta file describing what is probably just one edition of the magazine. If we scroll through a little bit, we can see a whole heap of URLs pointing to various assets, probably the assets that the app automatically downloaded as soon as I opened it for the first time. And in total, we've got going on 700 lines worth of this data. So this is starting to tell us quite a lot about how the app is put together internally. Let's drill down and take a look inside that assets folder and see what we can find there. Looks like we've only got styles. We'll drill down into that guy. And here we have a whole bunch of gallery underscore image folders. So clearly this is some sort of convention for how whatever entity number 4300 is actually put together. We'll just drill down into one of these just for a bit of a look. We might even just jump down into tablet. Only one folder in here, we'll grab public. And here are a bunch of images. So clearly this would be the content that goes into the magazine. So what it's actually looking like is what I've kind of alluded to already, in that the app is downloading entire editions of the magazine. We've got a bunch of photos here that look like they should be part of one of the articles. In fact, if we go and grab one of these, we can see the dimensions. So about 1500 pixels square, which is a pretty reasonable size resolution. It's certainly not a thumbnail. And a whole bunch of images here that look like they're all part of the one article. They've all got the same vehicles and a few other photos here that I would expect to find if I opened up the Evo mag. So let me wrap up what we've seen here by using Fiddler on this app. What we've learned that was never visible just by opening the app is that it goes and downloads everything. You get a whole bunch of editions of the mag sucked down over your bandwidth to the full extent of 1.8 gigabytes worth of data, and the whole thing saved already. What's more, you could always just go and grab this over HTTP yourself. A more nefarious individual might say, hey, I could just stand up my own Evo mag. All I have to do is create a website that requests the resources off their site, and there you go. Now clearly, that then becomes a security risk too, because suddenly you're circumventing the access control, which is that only authorized subscribers should have access to the mag. This is not a freebie. Now, as I said earlier on, this clip is a bit of an intro into the sorts of things that I discuss in my new Pluralsight course called Hack Your API First. Now that's a very security-focused course. So let's now move on and look at one really simple little security example, which is a great demonstration of what we refer to as a client-side only access control. Let's go and take a look at that now. I'm going to open up the British Airways app. It looks like this. Now here's the thing with this app. If you're a member of the British Airways loyalty program, their executive club, and you're of a sufficient status, you can get access to their lounge Wi-Fi passwords. Only if you are a member and only if you are of sufficient status. However, let's take a look at what happens as soon as we open this app. So I've just downloaded it, installed it on my phone. This is the first run. And we can now see a bunch of requests going out through Fiddler. So again, Fiddler is watching what is going on in the background of this app. The requests that you can't see because you don't have an address bar, you don't have developer tools or anything like that in the app. You have to proxy the data to see it. I'm just going to make the URL column a little wider. And now I'm going to go down and select the fourth row here. You can see that the URL has the word lounge in it, and it's a .dat file. So we'll select that guy. Again, the response is encoded, it's gzipped, so we'll go over and decode that response. Let's now go and just hit the raw tab, just so that we can look at the original contents of this file without any formatting. And what we see here is a bunch of response headers. And then down a little bit further, this is the body. And the body is all the Wi-Fi passwords for the lounges. So even though we haven't authenticated, we've already been given the passwords. This is pre-auth. We're anonymous at this stage. All I've done is downloaded the app and opened it. Now this may seem fundamentally simple, but I see this sort of thing happen all the time because inevitably the developers have worked on the assumption that they own the entire ecosystem. They own the app. They own the API. These two things are only going to talk to each other in the way they've designed it, and they're not expecting anyone to actually look at the traffic. Now, British Airways gave this to me. All I did is open their app and they served it up to my device. So clearly, they really weren't thinking through the process of how this data should be secured. Now, yes, it is only Wi-Fi passwords, but I've seen similar risks even in banking. It happens all the time in mobile. And that's exactly what the Hack Your API First course takes you through. What are the at-risk patterns? How do we find them? How do we make sure we don't build them in our own apps? Because if you can't hack your API first, somebody else will.